Hello, my name is Emma Stump, and I have the privilege of being on a research team with Tom Kincannon, Neil Singh, and Cho-Won Park, under the leadership of Jinji Luo and Professor Guo at Purdue University. When we entered this semester, the Guo Labs had finished publishing a paper called Focal Split, which is a low-cost depth from differential defocus camera mapping system. The product is based on the eyes of a jumping spider, which has two lenses that help it differentiate depth in its environment. Based on this, the Go Lab successfully created a depth and confidence map to a tethered camera by implementing an algorithm. The system, though, was not low power enough, and so our team sought to further this project along by implementing the same algorithm on a low power microcontroller, making steps towards live monitoring of both depth and confidence map. We first chose the best microcontroller through experimentation. Then we implemented the algorithm on Python. Then we worked to interface with the Sony ExpressSense board to perform the algorithm, and we worked towards video monitoring by successfully getting a serial output of the Laplacian calculated completely on the board to output to a host computer through USB. And lastly, we worked to create the confidence map to verify our results.
All right. Hi, everyone. My name is Neil. To begin, I'll start talking about the Python implementation that we have of focal track. So we start off by declaring some of these global constants, pixel pitch, sensor distance, and a Gaussian kernel. These variables are all specific attributes that are dependent on the physical camera setup. And so pixel pitch is effectively the distance between sensor pixels, and it lets us turn those pixel-based measurements into real-world units that we can actually use, and ones that we're more familiar with. Sensor distance is effectively just how far the sensor sits from the lens. And in a deformable camera lens, that's an important feature, especially when running focal track, because a lot of the later computation steps involve capturing the same scene just at different focal planes. And so that sensor distance value is important. And then the Gaussian kernel is how the point spread function, which models how the camera is the system's point spread function, which models how the camera blurs when slightly out of focus and whatnot. And so we pull in all these other sort of constants from the configuration file, which contains weights that are used to scale and combine our blur with other terms that are all in like later steps of the computation, specifically like the calculation for V and W. And so now that we've established some of those constants, I'll take you through the actual execution of code. So the first thing we do is we load in our pickle data set, and then we call load data, which unpacks our pickle data set into camera parameters like this, and then it also unpacks them into the focus shifted images, so which are important in calculating later steps in focal track. So then after that, we call compute depth and invoke that function, which effectively the first thing it does is it builds the defocus difference signal between the two focus shifted images, which is IRO-T. And then after that, it computes a Laplacian of the image using the Gaussian kernel and pixel pitch. And that effectively just to account for edge detection. And then for each pyramid, we sort of define it at one scale here. But for each scale of the pyramid, the Laplacian is resized and divided by the defocus signal, and that just helps store the raw like depth map, and then storing the median across like all the scales as the final depth. And then after that, we call filter depth map, which effectively just sorts the confidence values and masks out any depth estimates below our camera threshold. And then back in main, once we return all of this, we then visualize the actual filtered depths to a realistic range from 0.4 to like 1.4 meters, which we define here. And then after that, we plot it, and that basically just gives us a visualization of the depth map. So this is a relatively sparse depth map. You're not seeing too many colors, and that ultimately comes down to two things that we can kind of change. So the first thing is this confidence threshold, which is currently set at 30%. So if I were to increase this to 70%, and if I were also to compute this at multiple Gaussian levels, so 3 was effectively the max that we had, then you'll see a little bit of a different image, one that has a little bit more color, and a little bit more detail. And so these two steps are things that we're going to have to focus on integrating later with the ExpressSense.
All right, so where we kind of ended off was we were able to get some video to stream and then communicate that data serially from the Expressence microcontroller into the computer, and into my laptop, so we can sort of view a live video feed. So this is the code that I have running on the Expressence board right now. So let me just reflash that real quickly. So this is just this setup here. It does some initialization for the microcontroller, and then most of the code that really is doing the brunt of the work is in this camera callback function, which is called every time a new frame is available from the microprocessor. So we take the image, we convert it into grayscale to make the size of the size of the data that we're working with smaller. Um, we downscale it to make that data send quicker, in order to get a frame rate that is reasonable. And then here we calculate the difference of the last two frames. We calculate the Laplacian of the last two frames individually, and then we take the average of those two frames, and that's what we're displaying. Um, that's what we'll display in a second. So if we look at this Python file here, I have running off of my computer. This is just going to read the data coming in serially. So if we run this, there we go. So this is a live feed of the camera. This is me in the video. Hello. And yeah, what you're looking at right now is every frame is going to be the average of the past two frames with a Laplacian operation performed on them. So yeah, that's pretty much what we have.
Map. So for our focal track and focal split implementation of the confidence map, we use the absolute value of W to determine the confidence values for the depth map. As you can see here on the Python implementation, we use the filter depth map function to filter out the depth map given the confidence map that we have. Here you can see the threshold of the filtered map. As an example, if I set the threshold to 65, this will be the output of the whole filter depth map. And now if we do 85 and increase the threshold, you'll see that the details on the fish has disappeared as the threshold has gotten higher, so we'll filter out those pixels that we're less confident about. Now in our microcontroller implementation of this depth map, we have still used the same W, the absolute value of W, to determine the confidence and the confidence map. However, in this applied confidence function inside our Arduino, we try to use a histogram sort of the depth map instead of all the pixels, the depth value of each pixels, to reduce the load and memory capacity of this workload. You can see we also can change the threshold from 35 to 15. And to see the actual output value, since we use the SD card, I'll show you the saved result right now. This is the output of the filtered depth map using the 65 or the top 35% of the confidence map threshold. This would be the top 15 or 85% of the threshold, the same as we have seen before in the Python implementation. As you can see, also the details in the fish has disappeared just as it did on the Python implementation. Indirect result because of the higher threshold, making us lose the pixels and the details of the fish. Now, finally, to talk about what we have accomplished and what the next steps for the projects would be. What we have accomplished right now would be the whole implementation of a one-scale filter depth map with confidence map thresholds. What we can do next and the next steps for the projects would be to increase the scales as is in the Python implementation, where we go around the range of scales and downscale it every time with each scale to get a more in-depth information of the confidence map. Due to the limitation of our time and also the memory inside the microcontroller, we haven't been able to implement this on the low power microcontroller, but trying to make it as efficient and also in-depth as possible would be our next step. And also, using the full capability of the Sony Expressence board, if we can make a dynamic video type of the depth map with a constant stream of frame rates would also be a great step forward. Thank you.